again, welcome back. The main topic for this particular week is spatial autocorrelation. So, just first off, again, I hope everybody is safe, everybody is home, everybody is healthy. In terms of the labs, this topic does have a lab, which instructions will be posted on eCampus. And again, with the forums, you can ask questions about that in the appropriate forum. This is to explain the principles, the concepts of spatial autocorrelation. Now, if you recall, before we left, we had the principle, the idea already of spatial autocorrelation, of things are similar to their neighbors. Now, recall, again, that depending on what we are studying, we may choose different definitions of what is my neighbor. We could choose, for polygon data at least, we could choose, do they share a boundary? Okay? We could choose, are the centroids of the polygons or points within a certain distance threshold, whether or not they share a border. Or we could say, just give me the 5 closest, or the 10 closest, or the 3 closest, or whatever you choose. And I don't care if they share a border, I don't care how far away I have to get to reach that number. So the 3 different ways of defining a neighborhood: adjacency, nearest neighbor, and a distance threshold. However you do that, however we get our neighborhood, we then want to study spatial autocorrelation, or formally test whether or not the value here is similar to the values of the neighborhood around here. So I have already up here the general framework for statistical inference testing, and I will go through and put this in the context of Moran's I, or spatial autocorrelation. So first off, identify a question. That's basically already done. Are the values in my neighborhood related to the values here? And I did do a slight change. I said similar to, and just talking like, are the values like here? Versus here it just says, are they related? Recall that we could have the setup of the values are similar, which is positive spatial autocorrelation, and by far the more common of the two. Or if they're dissimilar, think about a checkerboard. White squares are always adjacent to black squares. I know my neighbors are dissimilar from where I am at. That would be negative spatial autocorrelation. The null hypothesis is that there's no relationship. Again, that's the kind of the boring default situation, even if the default situation is not very common in geography. The situation of there's no relationship. That is the null hypothesis. The alternative hypothesis is that they are related in some way, shape, or form, one to the other, whether that is positive or negative. The statistic that we will be using here, there are more than one, but the one we'll be using here is called Moran's I. It is far and away the most frequently used test for spatial autocorrelation. The way it works is just a correlation. It's the correlation of, you find that you get the value here, you find the average of the neighbor's values, however those are defined. I know I have two variables, the value here and the value in the neighborhood, and do a correlation of those. If you haven't seen correlation as a statistical approach here, that's fine. That's actually part of the next topic. There's, as we'll see, the regression and the Moran's I topics are very interrelated, and so it's kind of a crapshoot as to which one actually gets introduced first. I've chosen here to introduce spatial autocorrelation and Moran's I. So I get that correlation. Okay, I might find that value 0.2, 0.4, whatever it is. By itself, that doesn't tell me a whole lot. I want to know what the distribution is if there's no relationship, to be able to make that statistical comparison, evaluating the null hypothesis. So I find the distribution, Moran's I is close to a normal distribution under that null hypothesis of no relationship. However, strictly speaking, it is dependent upon the definition of neighborhood. And so we can't say automatically it is normal. Even though it's close, if we were still able to use ArcGIS and do Moran's I in ArcGIS, it would actually assume it's normal. But we're not doing that. We're not using ArcGIS. We're using a different software package called Geoda, which, again, installation instructions for Geoda will be the first part of the next lab. And it runs Monte Carlo simulations. It goes in what it does for those simulations. Takes the values. So if we're looking at, say, cases or the rate of COVID-19 throughout West Virginia counties, I have 55 values. Some of them are still zero, at least based upon reported cases. Some of them are much higher. I have the rates. And if I want to know, okay, is there a diffusion process? If the COVID-19 infection would be spreading from Mon County to Preston County, to Marion County, to Wetzel County, to our neighbors, then I can assume that those values will be related to each other. That an infectious process would create spatial autocorrelation in the positive sense. So if I wanted to go and test that, I could scramble the values. So a way of saying there's no relationship is to just throw the values in the air, see where they land, in a sense. I take Mon County's value, assign it to Preston County. Preston County's value goes to Wood County. Wood County's goes to Berkeley County. Berkeley's goes to Mingo. Mingo's goes to Kanawha. Kanawha goes to Pleasance, and so on and so forth, until all of the values have been randomly reassigned. If they're randomly reassigned, I can assume there's probably no autocorrelation there. And I do that, scrambling 999 times, or whatever you pick, probably 999. And then I have those values, and I can compare the actual value to that. By finding how many or what proportion of the scrambled values representing no autocorrelation at all are above for positive autocorrelation or below for negative the actual value of I. Based upon that, I divide that by the total number of simulations plus 1 to get my p-value. So it's saying, okay, I found 5 out of the 999 exceed the actual value. 999 plus 1 gives me 1,000. That's why it's 999 instead of 1,000 to begin with. 5 over 1,000, 0.005. That would then, therefore, be my p-value for this test. Representing that is the probability, the null hypothesis, the probability that there is no relationship between a county or a place and its neighbors, is supported by the data. And that's, given the example that I used here, COVID-19 rate, that is a very critical piece of the puzzle here, recognizing that because of the limitations in testing, there are not testing facilities covering all parts of the state, that in many cases we may have, well, we're guaranteed to have an undercount of the total number of cases. In some cases, in some places or counties that are far from testing sites, that could be a dramatic undercounting of the number of cases. So the data in this situation we know is imperfect. And so even if we were to find no autocorrelation, unrelated, we would say that's the extent to which this data supports that null hypothesis, as opposed to our complete and total belief that the null hypothesis or the alternative hypothesis is correct. Regardless, at the end we still choose whether to confirm or reject the null hypothesis, and do I believe that there is autocorrelation, and take action upon it. If, say, there is autocorrelation, we may then want to take action of setting up makeshift additional hospitals. Like if Monte County is one of the hotspots for West Virginia, perhaps converting the WVU Coliseum into the hospital type setting to provide additional capacity, recognizing that there's going to be a lot of cases here. So that's the overall process of spatial autocorrelation. What I'll do next looks at a couple of these steps, especially this part, how Moran's I works, and getting the p-value. So, as you will see when you do the lab, one of the first things that comes up when looking at Moran's eye, when looking at spatial autocorrelation, you will see a scatter plot. Along the horizontal axis is the value at that count here, at that place. And along the vertical axis is the average value of the neighbors. However, again, we have to find neighborhood. The situation I have here would be probably a fairly typical situation of positive spatial autocorrelation. Where, if I draw a line through this set of points, we see that it goes up. It has a positive slope or positive trend. As this value goes up, so does the neighbor's average. So there's a positive relationship here. That doesn't mean it is complete perfection, but there is a noticeable relationship there. If that red line, I'll draw in pink with dashes for these other hypothetical situations, and I'll mark out this as positive. If there is no relationship, it would be flat. There would be no relationship. If it points down, that would suggest a negative relationship, negative autocorrelation, where if the value at a county is high, the neighbors have low values. And if the value at a county or an observation is low, its neighbors have high values. That would be negative. In this case, as I have drawn the blue dots, if the value is low, its neighbor's average is low as well. Likewise, if the value is high, the neighbor's average is also high. So I do this, and I might get a value for I, 0.276, let's say. Okay, so what? What does that actually mean? That is my value of the test statistic. Now I want to compare against the distribution of what I would expect I to be if there is no relationship. As I said, we're using in Geoda a Monte Carlo simulation for that. That Monte Carlo simulation is going to give us a histogram of all of the values from the 999 scramblings. As I said, it's going to look pretty close to normal, but probably not quite. The ends are a little bit fatter than a normal distribution would be. So I have this. It's going to be centered somewhere in the general vicinity of 0. Again, because the random data, not a perfect mathematical formula, it's not going to be exactly 0, but it's going to be close. Then, okay, I find where in this histogram does 0.276 lie. It could be at the very top. If it's at the very top, nothing is above it. Divide by 1,000 total values, the 999 in the purple scrambled histogram, plus my actual observation. My p-value therefore is basically 0. Okay, then I know there's basically no chance that this is random, that this has no relationship. If this 0.276 is within the histogram, then I look and see how many in the histogram are about. Okay, as I wrote there, maybe it's 13, or that gives 1.3%, 0.013 as my p-value. As my actual value gets closer and closer to the middle of the histogram, I have more and more support for the null hypothesis that a county's value or an observation's value is not related to those of its neighbors. Now, this is all well and good as far as it goes. And it could, if we're dealing with a disease without much understanding, then it could tell us, well, is it contagious or not? Is there an infectious process or not? That said, we know that for COVID-19, mind you. This could tell us that. However, there is a very big piece of the puzzle that is missing if I want to take action. Because knowing something is contagious, okay, then yes, I may then wish to identify where should I send extra medical equipment, medical supplies, extra ventilators, extra masks, extra personnel. If I don't know where the high values are clustered and where the low values are clustered, then I don't have enough information to actually take proper action. So in many cases, this spatial autocorrelation, Moran's eye, is followed up with a local spatial autocorrelation. The official term ends up being local indicators of spatial autocorrelation, or LISA, or you may hear just as easily local Moran's eye. What local Moran's eye is doing is taking that scatter plot, and it is saying, or asking, how unusual, how away from these center lines is each individual county. And so I'll put up a county, or outline at least, of West Virginia. Very crude, as usual. So Monte County has 4 neighbors. I can then say, okay, where in here is Monte County? It might be the one I just circled there. Does that constitute part of a cluster of high values? In this case, it probably does. It's not the absolute highest, its neighbors are not the absolute highest, and on a per capita basis, Monte County probably isn't. Yes, it has the highest number, but it also has one of the higher populations in the state. So the average rate's probably kind of middle. Still pretty high, but not necessarily the highest. So okay, I find that for local Moran's eye, the results are going to be mapped. Anything that is high values next to other high values, let's just say for the sake of argument, they're mapped in blue. That includes Mon County, it would include others. We can have low values surrounded by low values. That also typically goes with the territory for spatial autocorrelation. So there might be I don't know. Let's say for the sake of argument at least, I don't know the exact status here, maybe Jefferson County is low and Berkeley County is low. That would put Jefferson County in a low category. You'll notice the way I drew it, there are a few counties, a small number of counties, that actually don't quite fit that trend. These are the counties that are unlike their neighbors. You can have a few of those and still have an overall pattern of positive spatial autocorrelation. That's illustrating that Moran's eye especially, it's evaluating the entire state, the entire data set as a whole. There can be observations that don't fit that general trend. Wetzel County, I know, does not have any cases, at least as of yesterday. I haven't seen today's report. Thanks especially to Mon County and possibly to Marion County as well, and maybe Marshall County to its north that has a small number of cases at least. Wetzel County could be it is itself low, but is surrounded by high values on average. So it is low with high neighbors. Again, for the sake of argument, because I haven't mapped out the cases exactly, Berkeley County might be, it can have a high value itself, but its neighbors are low. So it would be a high to low outlier. This is true. So there are, in local Moran's eye, 4 situations where a county can be deemed unusual. It can be deemed to, in a sense, deviate from the closest thing local Moran's eye comes to a null hypothesis, which is that a county or its neighbors or both are average. Something important to note in what I just said, a county or its neighbors or both are average. if I put a point out there at the very high end, even though it has the highest rate of any points there, the highest rate of any counting, that does not automatically put it into a cluster if its neighbors are not particularly high, nor does it guarantee that it is an outlier because its neighbors are not particularly low. Its values are out. The neighbors are average, and so it does not go into any of the 4 categories. So that is local Moran's eye. Its output, it'll be an entire map like this with 4 different colors. The way Geoda gives is 2 shades of blue and 2 shades of red. I don't have that very easy, so I have red and pink and blue and purple. And again, I hope that you all have, if you have questions, you ask them. The one last thing, because this is not a cartography course, as with the point pattern, there will be some expectations for the communication aspect in the cartography, but it will not be the same as you may have seen if you have taken digital cartography with Dr. Maxwell. And as with other labs, I will spell out what I would like to see in the map. I will spell out what I would like to see in terms of the values that are presented for a report. So again, if you have any questions, please ask on the forums on eCampus. And finally, again, I hope everybody has been washing their hands. I hope everybody is safe at home. If you have any problems, I don't know that I cannot force you to wash your hands, but I hope everything is well for you. If anything prevents you from making progress on the course, please let me know through email, through eCampus. So as far as the videos are concerned, unless there are any follow-up questions on eCampus and the forums that would benefit from more drawing on the board, I'll virtually see you next week with the next set of videos. So take care of yourselves. Have a good week.